Good morning. I welcome you all to this session of fluid mechanics. Last class we were discussing the application of dimensional analysis, that is Buckingham's Pi-Theorem, in pi flow problem to recognize the different dimensionless terms as the similarity criteria. And we arrived at this, if we recall this, a pi flow problem. This is the flow. We have found out that delta P by L per unit length is a function of flow velocity V, the hydraulic diameter dH, which is the pipe diameter in this case. dH is the pipe diameter or hydraulic diameter, rho, and the viscosity mu. Or this can be delta P by L. So delta P by L V dH rho mu is 0. That is the implicit functional relationship, that these are the variables defining the problem, where delta P by L is the output parameter, dependent variable, which depends upon velocity of flow, hydraulic diameter, and density and viscosity. So according to Buckingham's Pi-Theorem, we see that number of variables m is 5, and number of fundamental dimensions in which these variables can be expressed is 3, that is MLT. Then the number of pi terms according to Buckingham's Pi-Theorem is m minus n, that is 2, 5 minus 3 in this case. So 2 pi terms will be there, pi 1 and pi 2. Now according to this theorem, we will have to choose 3 repeating variables. Now there are 4 variables excluding this dependent variable, that means 1, 2, 3, 4. So number of choices are there, and we have seen that if we choose V, dH and rho, 3 as the repeating variables to determine the pi terms as per as the procedure, then we land up with the conventional friction factor and Reynolds number as the 2 pi 1 pi 2 terms, not Reynolds number, 1 by Reynolds number. Now we will show that if we take any 3, that means another set, there will be 4 sets, and what will be the pi terms or the dimensionless terms. See that if we take repeating variables V, dH, rho, we will end up with this pi 1 and pi 2, that is, this is pi 1 and this is pi 2. So this is the conventional friction factor, this is 1 by Reynolds number, and functional relation is function of this and this 0. That means this is a function of this. Anyway we can take. But if we take V, dH, mu as the repeating variables, we get a different dimensionless term. So this will be just 1 upon this, reverse, and this will be this is also a dimensionless term. If you calculate the dimension of this, it will be dimensionless. So the functional relationship of function of this and this is 0. Similarly, if we take these 3 as the repeating variables, we get this 2 as pi 1, pi 2. If we take these 3 as the repeating variables, we take these 2 as pi 1 and pi 2 terms. So that the functional relationship is like this. So this way we take the repeating variables like this. So if we, now the question is that this way if we take the repeating variables, we are landing up with different pi term. Now the pertinent question comes, how should I know that which pi terms we have to take to get the correct result? The answer is like that, all the pi terms are physically, mathematically meaningful, physically also meaningful in maintaining the dynamic similarity criteria. And you see, these sets of pi terms are not independent, they are interdependent between each other. How? Just you see, it is very simple, that if you compare the pi terms of 1 and 2, if you compare the pi terms of 1 and 2, let this is set 1, let this is set 2. Then you see the pi 2 of set 2 is 1 by pi 2 of set 1. That means if you make the reciprocally, please don't talk in the class. If daily I will have to tell that, just like a schoolboy, I am sorry, this videotape cannot be made for the outsiders. I just beg pardon to the outsiders that if every day, just like a kindergarten school, I have to tell IITians don't talk in the class, I am sorry, I cannot take this class in that class. Otherwise you leave the class, then I will go on teaching for outside students. I don't want you. If you like to talk, you please go out. So I cannot take a kindergarten class that each and every day I have to come to the class and tell you please don't talk. I am sorry. 1 by pi 2 of set 1. So you see that pi 2 of set 1 is 2. This pi 2 of set 2 is 1 by pi 2 of set 1, or rather I can write that pi 2 of set 1, rather 1 by pi 2 of set 2. Similarly, pi 1 of set 1 is nothing but pi 1 of by pi 2 of set 2 of set 2. That means if I divide this one by this pi term, I get this. That means I can tell that if I get a functional relationship of pi 1, pi 2 is 0 from set 2, that means this set. And if I tell another functional relationship of pi 1 by pi 2 from set 2 and 1 by pi 2 is equal to 0, I arrive the set results for set 1, because pi 1 by pi 2 is this pi term, pi 1 of the set 1 and 1 by pi 2 is the pi 2 of set 1. That means from set 2 I can go to set 1 just by some combinations of pi terms. So this has become a rule or a corollary that if we land up with any number of pi terms, a combination of these pi terms will also be a functional relationship, will a valid functional relationship, keeping the number of pi terms same. So you will see this way, some sort of combinations between this pi term will be, that means this pi 2 same as this pi 2, but 1 by this pi 2 is equal to this pi 2. You will see some combination with this will definitely land up with this. If you divide this by this, you will get this, or you will make some combination between these two, we will get this one. So therefore we will see that we will get any of the sets of pi terms from other sets by some recombination of the existing pi term. That means if we take any 3 repeating variables, we will be landing up with the different pi terms, but all the results are equally correct because these pi terms are interdependent pi terms. So therefore there is a corollary of the pi theorem that if there are number of pi terms, pi r number of pi terms, which is m minus m is the number of physical variables in the fundamental dimension in which they can be expressed, then this is similar or equivalent to another functional relationship of any combinations like pi 1 pi 2, pi 1 by pi 2, pi 3 to the power half, any such combinations, but number of pi terms will be same. Just like this, pi 1 pi 2, so this is equivalent to pi 1 by pi 2, 1 by pi 2. But the question comes, in all the cases, the non-dimensional terms may not be physically meaningful. For example, here the second term here is Reynolds number. So here it is 1 by Reynolds number. However, this is true, but in this case, these 3 sets, these dimensionless terms, though they represent the dynamic similarity because they are interdependent through another pi term, but they don't have physical meaning. These have the physical meaning and is equal to the friction factor. That is the only difference. Now next, I like to solve one interesting problem before I switch over to another problem or another analysis. Example 2, you see that this problem, a torpedo shaped object, I am going very fast because this is very simple, of 900 millimeter diameter is to move in air. This is a problem done in my book, but still for more explanation, to explain it more, I just do it here, is to move in air at 60 meter per second. This is the actual condition, that a torpedo shaped object of 900 millimeter actual diameter is to move in air. This is the velocity of the torpedo, is actual condition, and its drag is to be estimated. So under this condition, the drag force to be estimated from tests, that means test in laboratory in water. So test has to be made in water, not in air, on a half scale model. So laboratory water is available because the flow of air is difficult to create, but the flow of water may be easier to be created. So therefore it is done on a half scale model, that means size will be half. Determine the necessary speed of the model. So under this condition, what should be the speed of the model? That means the speed of the torpedo in the laboratory and the drag of the full scale object if that of the model is this. That means what should be the speed of the model, you have to first find out, and at that speed for a test under water, if the measured drag in the laboratory is 1140 Newton, what should be the drag of the full scale? So viscosities of air are given, densities of air and water. Viscosities of air and water are given, densities of air and water are given. These are the properties to be required. Now you see this problem has to be first identified, that the drag of the torpedo, that means drag is F, this becomes a function of velocity of the torpedo V, the diameter of the torpedo D obviously, and what are the other things? The velocity, the diameter of the torpedo, and the density and viscosity. So therefore drag depends upon the velocity, the diameter of the torpedo, the density and the viscosity, and this is the function of this. Or we can define that the entire problem is guided by this variable. This is the output variable. First we write the dependent variable is a function of this independent variable. So in all, including the dependent variables, these are the implicit function by which this phenomena can be expressed. That phenomena of drag while air passes or air flows past the torpedo is like that. The drag force, flow velocity, diameter of the torpedo, density and viscosity, functional relationship is equal to 0. Now therefore, if we apply Buckingham's pi theorem, first we see how many variables, 1, 2, 3, 4, 5. So m is equal to 5. So number of fundamental dimension in which these variables can be expressed, there is no temperature, only mass, length and time, so 3. So therefore number of pi terms is equal to 5 minus 3. So how to determine 2 pi terms? First of all, we have to consider the variables, that is repeating variables. If we take V, D, rho, these 3 as the repeating variables, because the choice is between these 4. Again number of choices will be there, but usually we take V, D, rho, one with the geometric dimensions, one with the flow characteristics. The flow velocity is there, these are the rules, thumb rules. Flow velocity should be taken. Another is the rheological properties, preferably rho or other mu. Better you take rho, V, D, rho. Then the procedure is that first pi term will be unknown integer exponent V to the power A, D to the power B and rho to the power C, and one of the remaining variable, let A. And another will be V to the power A, D to the power B, the other remaining variable means. So automatically number of pi terms it will match. So all the remaining variables apart from the repeating variables have to be multiplied with the repeating variable raised to the power unknown arbitrary indices. So number of pi terms will automatically match, because there will be two rest. There will be two rest, that means out of these 5 parameters, if 3 are taken as repeating variables, so 2 variables will be left, so there will be 2 pi terms. Now if I express the dimensional analysis, now I do the dimensional analysis, this m0, because pi 1 is a non-dimensional term, so V is Lt to the power minus 1 A, D is L to the power B, rho is mL to the power minus 3 C, and F is mL T to the power minus 2. So therefore if we equate, then you get C plus 1 is equal to 0, C plus 1, then with for the L, A plus B minus 3C plus 1 is equal to 0, and for T minus A minus 2, okay, is equal to 0. So therefore if we solve it, you will get A is equal to minus 2, D is equal to minus 2 and C is equal to minus 1. So if you put it, you get the pi 1 term as F by rho V square D square. So this is one pi 1 term. Similarly, if you solve for pi 2, this if you put this L by L T to the power minus 1 to the power A, L to the power B, m L T to the power minus 3, same thing, only mu is m L T to the power minus 1. Okay, let us write, why unnecessarily. So for pi 2, if you write it, so pi 2 similarly m to the power 0, L to the power 0 is equal to L T to the power minus 1 whole to the power A. So D is L to the power B. So rho is m L to the power minus 3C, m L T to the power minus 1. If you equate it, so you will get A is equal to B is equal to C is equal to minus 1. You have to get it. And therefore, you get pi 2 is equal to ABC minus 1 means if you put it here mu by rho VD. So mu by rho VD. So therefore, what is done first, first the pi 1 and pi 2 terms are recognized. So therefore the problem is now defined as f by rho v square d square, it's a functional relationship of some phi, f by rho v d by mu, mu by rho v d we can write like that, mu by rho v d is equal to 0. Or we can write f by rho v square d square is a function of, just I can make a reverse, rho v d by mu. That means this is known as drag coefficient, conventional drag coefficient. That is drag force divided by the dynamic head, 2 is not there, rho v square, times the square of any characteristic dimension. So that is a function of Reynolds number. So therefore what do we do? First we reduce the problem in terms of dimensionless parameter. That means drag force, velocity, diameter, density, viscosity, we club it. So CD as a function of Reynolds number. Now you see that for model testing these parameters have to be kept fixed. So first criteria for model testing is that Reynolds number have to be kept fixed. So therefore Reynolds number for the model, if I give the subscript for the model, must be equal to Reynolds number for the prototype. That means you are allowed to do the experiment with water. You are allowed to do the experiment with different diameter, but you have to make this combination, that Reynolds number same for dynamic similarity. So if you make this, so if you know the diameter ratio from the scale factor, you can find out the model speed. That means we can write from here that Vm, that model speed, what is the answer? The Vm is equal to Vp, okay, dP by dm into rho p by rho m into mu m by mu p. So if you put this value, Vp is given, that is actual velocity is 60. Now scale factor, half scale model, that means laboratory scale is half, that means dm by dp is half. So this is 2. So rho p by rho m is the density ratios, that is 1.20 divided by 1000 as it is given, density of air, density of water, and mu m by mu p, that is the viscosity of air, water, model is the water, model fluid is the water, and this is the viscosity of air as it is given, that is the prototype, and you get this is equal to 7.82 meter per second. That means we will have to make the experiment under identical Reynolds number. Now what we do, we find out the CD from our laboratory, and from that CD we decode the drag force in actual case. So therefore what is meant, that the CD also will be same. If the Reynolds number is same, so whether it is a model test or prototype, because CD is a function of Reynolds number, when Reynolds number assumes a unique value, CD will be assuming the unique value. That means the CD in both the cases will be same, or in other words these dimensionless terms also will be same in both the cases, which means that dimensionless terms, F, M, or rather P first I write, Fp, rho P, Vp square dP square is equal to Fm, rho M, Vm square dm square. It has to be same. From which I can find out Fp is Fm into dP by dm square into rho P by rho M. Okay. So into what is that? Vp by Vm square. So therefore if I know the drag force in the model, I can find it, this is 2 square, rho P by rho M is what? Rho P is 1.20 and rho M is 1000, and Vp by Vm, Vp is 60 meter per second and Vm just now we have evaluated. So therefore we get this Fp as 320. Now you see this problem explains two things very beautifully. First of all, how to obtain the similarity or dimensionless parameters by the use of Buckingham's Pi-Theorem for a particular physical problem. Then how to apply these non-dimensional terms for these problems between laboratory tests and the actual practice, where the problem is same, problem physics is same, but they are under altered conditions. Now I come to another very interesting situations, that if two variables in a problem are same in dimension, that means two length scale or two velocities, then their ratio will automatically be a pi term. Just an example I take. Remember the Couette flow problem. What we have discussed in relation to analytical solution of Navier-Stokes equation, that one plate is fixed, another plate is moving with a velocity u infinity. And we have found out, we have taken this as the axis and we have found out the velocity distribution with y. And this is also a problem where a dp dx, a pressure gradient dp dx is imposed on the problem. So if I define a problem like that, Couette flow problem, that one plate is moving with u infinity velocity, another plate is rest, and there is a dp dx pressure gradient which causes the flow. So you find u at any location y, that means u as a function of y. This we found out from exact solution of Navier-Stokes equation, and we have seen that how from the exact solution of Navier-Stokes equations we derive the expression in dimensionless form. Now let us apply the Buckingham's Pi-Theorem to obtain the same expression. How? You see that. Now here the problem is that u at any location is a function of the location itself, because u is a function of y. Oh, another definition, I am sorry, that is the plate spacing is h. So it will be a function of the plate spacing h, it will be a function of u infinity, that is the velocity of this plate, it is a function of dp dx, and it will be a function of the viscosity mu. Because this is a problem where inertia force is 0, so rho is not coming into picture. This is a physics of the problem that you will have to understand. This is of course difficult at this stage, so it is governed only by the pressure force and viscous force. So there will be mu only. So y, h, u infinity, dp dx and mu. So u depends upon this. That means we can tell that a functional relationship between u, y, h, u infinity, dp dx and mu defines the problem. This is the implicit functional relationship by which the problem can be described. So now if we apply the Bernoulli this dimensional analysis, first we write m is equal to 1, 2, 3, 4, 5, 6. N is equal to, what is n? What is n? 3, because MLT 3. So number of pi terms is equal to 6 minus 3, it is 3. So there are 3 pi terms. Now the choice comes with the what is that? Choice comes with the repeating variable. So u is the dependent variable, you exclude u. Better you take u infinity, h and y. U infinity is the flow characteristics and u not y and h, because this will be wrong. So two repeating variables should not have the same dimension. So u infinity you take h. So one with the flow characteristics I have told, another with the geometric characteristics, that better take h because y is a variable distance, better take variable dimension should not be taken, that way h, and another with the fluid property, here rho is not there, mu. So if you take these 3, then remaining other 3. So these 3 will define the 3 pi terms. How? You see pi 1 is equal to, what is pi 1? H u infinity mu. So you take u infinity first to the power a, h to the power b and mu to the power c, any one u. Pi 2 u infinity to the power a, h very simple, mu to the power c, another one left y, and pi 3 is equal to u infinity to the power a, h to the power b, mu to the power c. There is no other parameter left, so automatically it will take care of 3 pi. Now if you substitute the dimensional formula of this L by T, L T to the power minus 1, this L, M L to the power minus 1, T to the power minus 1, and this U is L T to the power minus 1. This way if you do, you see here this pi term will tell B is equal to C is equal to 0 and A is equal to minus 1. From this pi term you will get pi 1 is U by U infinity. Similarly from this pi term, if you work it out, you will get the same thing. If you work it out for the exponents ABC, the values of the exponent ABC by equating with the left hand side m0, L to the power 0, T to the power 0. Here also you will obtain for this A is equal to C is equal to 0 and B is equal to minus 1. That means Y by H is pi 2. But the pi 3 if you work out, you will see pi 3 will be H by mu u infinity into dp dx. Pi 3, which means B is equal to 1, you will get A is equal to C is equal to minus 1. So that you get this. Therefore, then you can tell that u by u infinity a functional. So therefore, we know that finally we replace the relationship as a functional relationship of the pi terms, pi 1, pi 2 and h by mu u infinity dp dx is equal to 0. So you can write u by u infinity is a function of h by mu u infinity dp dx and y by h. So I have solved this problem because of two reasons. One is that now you can see that by the exact solutions we have found out u by u infinity as a function of h by mu u infinity dp dx. Okay, h square by mu u infinity. I am sorry, this will be h square probably h square by mu u infinity. I am sorry, this will be h square by mu u infinity. I am sorry. So I am sorry, and this will be h square by mu u infinity. So therefore, this pi 3 terms where I have explained b, that b is equal to 2, h square by. But the difference is that the most interesting thing and informative thing is that by the exact solution of Navier-Stokes equation, we deduce the relationship. If you remember, u by u infinity is y by h plus h square by 2 mu u infinity into minus dp dx into y by h into 1 minus y. Now here the problem is that here we cannot express this explicit functional relationship. We can only recognize that this is the dimensionless dependent variable, this is one non-dimensionless independent variable, it is another dimensionless independent. So only the dimensionless variables, both dependent and independent, we can fix. But by Buckingham's Pi-Theorem or dimensional analysis, we can never find out the actual explicit relationships. For example, the earlier problem also, the drag force is a function of Reynolds number. What should be the explicit form of the functional relationship is very difficult to be established by dimensional analysis. This cannot be done. This has to be done either by a theoretical analysis or by doing experiments from the empirical points by regression analysis. Otherwise, the explicit relationship is not possible. But in comparing the results from model to the prototype, it is not necessary to have an explicit relationship. If we know the pertinent dimensionless terms governing the problem, it is all right. So therefore, one of the conclusion is that if two terms having same dimension, their ratio is automatically pi term. That means in defining a problem, if I see there are two variables of same dimension yh, so y by h will be a pi term. Similarly, two variables u here, u and u infinity are of the same dimension, u by u infinity is a pi term. So now I conclude the Buckingham's Pi-Theorem by telling this. What are the rules of Buckingham's Pi-Theorem? First, identify the problems by its physical variables governing the problem. That you will have to detect. Sometimes it is told, and in actual case it will not be told. For the purpose of examination it may be described. That is, a problem is described by these variables, physical variables. Then you have to find out, let m is the number of physical variables describing the problem. Then you identify the number of fundamental dimensions in which the physical variables can be expressed. Let this is be n. So then m minus n will be the number of pi terms or the dimensionless term describing the problem. Now to find out the dimensionless terms, you will have to fix the number of repeating variables. The number of repeating variables will be n. So there will be m minus n terms left. So choice of repeating variables will be like that. One should be flow parameter, another should be geometrical parameter, and another should be property of the fluid. then these 3 repeating variables, so pi terms is set by multiplying the 3 repeating variables raised to arbitrary unknown indices and the one of the rest dimensional variables. So this way m minus n pi terms will be formed, and then the values of ABC will be found out by equating the indices of the fundamental dimensions equated for the individual pi terms. Corollaries are like this, that if these 2 variables of a particular problem are of same dimension, their ratio will be automatically a pi term. Another thing is that if you land up with certain pi terms by choosing certain repeating variables, you can make a combination of the pi terms keeping the number of pi terms same to describe the same problem. Alright, you may see that you have not landed up with the conventional terms. Then you see some combinations will give you the conventional terms. Then you tell that this into this divided by this is also equivalent to that particular functional relationship, keeping the number of pi terms fixed. Now I will tell you what is Rayleigh's indicial method. Now next is the Rayleigh's indicial method. So there is another method known as Rayleigh's indicial method in determining the problem, in determining the pi terms dimensional analysis. That means in determining the pertinent pi terms for a problem. So just like Buckingham's Pi-Theorem, Rayleigh's indicial method I will describe. This is also based on the dimensional homogeneity of the physical variables involved in a problem. So what Rayleigh's indicial method does, it recognizes, for example, a problem is defined as x1, x2, x3 ... xm number of variables. So what it does, it first recognizes the dependent variable or output parameter and expresses this as a power law type of relationship, some constant a, x2 to the power a, power law type of dependency or power law type of dependence with the dependent variables. That means with the independent variables, sorry, that means in Rayleigh's method we first recognize the dependent variable and express the dependent variable as a power law product of the indices, product of the independent variable raised to unknown indices with a constant, multiplying with a constant. Then these unknown indices, what happened, we have got, if we equate the m, l and t from right hand and left hand side, we have got 3 constraining equations. 3 constraining equations. That means that if we have a number of unknowns, for example here if m is this, so m minus 1 unknowns will be there, a, b, c, like that, because dependent variable is here. So m minus 1 independent variables, if total variables are m, so m minus 1 unknowns, but we have got 3 constraining equations. So these 3 equations are eliminated. So m minus 1 unknown, they are expressed in terms of 3 variables, less than 3 variables. So 3 variables are eliminated for m minus 1 unknowns in finding out the grouping of the pi terms. So this is the key point of the Rayleigh's indicial method, or the central role of the Rayleigh's indicial method. Let us describe the Rayleigh's indicial method for a pi flow problem, then only it will be clear. What is pi flow problem? Pi flow problem, we know that delta p by L, function of delta p by that pi flow problem we just defined like this, dh rho mu 0. So the first problem which I solved, that this is defined, described by these 1, 2, 3, 4, 5 variables. Now Rayleigh's indicial method does like this. They first identify the dependent variable, and it starts with that let delta p by L becomes a function of the independent variable of this nature, b to the power a, dh to the power b, rho to the power c, mu to the power d. Let us express, or let us assume that delta p by L becomes this type of relationship, bears this type of relationship with the independent variables. Okay, then what it does in the next step, that equate the fundamental dimensions. What is the fundamental dimension? M L to the power minus 2 t to the power minus 2, a L t to the power minus 1 whole to the power a, L to the power b, m L to the power minus 3 whole to the power c, m L to the power minus 1 t to the power minus 1 to the power d. Now if we equate the MLT, you will get c plus d is equal to 1. Equating this, a plus b minus 3c minus d is equal to minus 2. That is L. A plus B minus 3C, and T for T minus A minus D is equal to 2. So here the difference is that if we express like this and equate the MLT dimensions, we will be always getting 3 constraining equations. But here we see A, B, C, D, 4 unknowns are there. So what we can do, 3 we can eliminate. That means we can express all the unknown in terms of 1. Let us consider that we will express all the unknown in terms of D. So what it comes? D, C is equal to immediately 1 minus D. A is equal to 2 minus D. And what? Please, there is any mistake? What is? Please tell, quick.
Minus A is equal to minus 2.
Minus A minus D is equal to minus 2. This is all right? Minus A minus D is equal to minus 2. These two are all right? Now, okay, C is equal to 1 minus D. A is equal to, what is A? A is equal to 2 minus D, and if you put C and D, you will get B is equal to, you will get B is equal to minus D minus 1. So everything is put in terms of D. Then I put here delta P by L is equal to A V to the power A, that means V to the power 2 minus D, dH to the power minus D minus 1, rho to the power C, that is rho to the power 1 minus D. So everything now is expressed in terms of D. Now this can be written like that. If we take rho V, that means this is separate, rho V square, and what is that? dH minus 1 by dH. Then we can club V to the power minus D, dH to the power minus D, rho to the power minus D mu, that means mu by rho V dH to the power D. So therefore it is done. Or you can write, if you multiply this, delta P dH by L rho V square is A into mu by rho V dH. That means I can recognize the dimensionless terms, but these AD values I do not know. I do not know the explicit form. This has to be found only from experiments or from theory. But I know that delta P dH L by rho V square is one variable in dimensionless form, which is the dependent variable, and independent variable is mu by rho V dH. This is the way the Rayleigh's indicial method does. That means it identifies the dependent variable and express the dependent variable as a product form of the independent variable raised to the power unknown integer indices multiplied with a constant. This is a style. This you can make one. This does not play a role in this process. Then equate MLT from both the sides. You get 3 constraining equations. Number of unknowns may be more, but you can eliminate 3. For example, here the number of unknowns are 4. So if you eliminate 3, you will be expressing in terms of only 1, and you can club it. If the number of unknowns was 5, we could have eliminated 3. That means 5 unknowns could have been expressed in terms of only 2 unknowns, and you will see that 2 unknowns are such that you can club the grouping for the pi terms automatically. So this is clear. This is Rayleigh's indicial method. Now another, so these 2 methods we have discussed: dimensional analysis by Buckingham's Pi-Theorem. Another is the Rayleigh's indicial method. But most interesting, or I shall tell the most easy method, is the Buckingham Pi-Theorem. Rayleigh's indicial method sometimes gives us problem, because if there are more number of pi terms, so a problem is governed by large number of variables, then what happens sometimes in eliminating 3 from the 3 constraining equations with a large number of unknowns may be a difficult job, and there is a chance of performing mistakes. So it is better to proceed with the Buckingham Pi-Theorem to recognize the dimensionless terms defining a problem. So therefore again I repeat the dimensionless pi terms, dimensionless the Buckingham's Pi-Theorem. First you recognize the number of variables of the system. Then you recognize the number of fundamental dimensions expressing that variables defining the problem. And then the number of pi terms will be m minus n. Here very interesting question comes. None of you have asked this. Sir, what happens if m is equal to n or m is equal to less than n? If m is less than equal to n, that means a problem is described by number of variables which is either equal to or less than the number of fundamental dimensions, then m minus n 0 or m minus n less than 0. So there is no pi term. That means no process is described by that. When m less than n is an impossible situation, and m is equal to n means this represents an equilibrium state of a system. So a process has to be described, m has to be more than n. So m cannot be less than n. So therefore m minus n will be the pertinent dimensionless terms defining the problem. Then you choose the repeating variables judiciously. Number is n, and these repeating variables must contain one flow parameter, another geometric characteristics, another, what is another one? One flow, one geometric, another is liquid property or fluid property. Then you go for finding out the different pi terms. If two variables have the same dimensions, their ratio is automatically a pi term. Alright, so this is all in discussing the similarity principle, and one must know that why we are finding out the dimensionless terms, because these are the terms representing the criteria of similarity. So if one has to make experiments in the laboratory to predict the performance for the actual systems operating under different set of conditions, yes, he can do the experiments under altered sets, but his dimensionless parameters, the dimensionless parameters between the two systems operating under different conditions have to be kept fixed to maintain the criteria of similarity. And moreover, the experiments that have to be performed is reduced, the number of experiments, because the influence of one variable will show the influence of other variables in a group, in a particular group. These are the two advantages of making use of the dimension analysis and through the Buckingham Pi-Theorem and Rayleigh's indicial method in developing this functional relationship between the dimensionless terms of a particular physical phenomenon. Thank you. Good morning. I welcome you all to this session of fluid mechanics. Today we will start a new chapter, that is flow of ideal fluids. We will describe here a brief discussion on the flow of ideal fluids. Now what is an ideal fluid? We have already recognized the definition. An ideal fluid is a fluid which has no viscosity, and therefore flow of such fluids known as inviscid fluids which has no viscosity is known as ideal flow. In addition to this non-viscous nature of the fluid, that means zero viscosity, we will impose here two other properties of the fluid, that incompressible, that density remains constant, and at the same time irrotational, the rotation in the flow of fluid is zero. So therefore we will mainly discuss the flow of an ideal fluid with incompressibility, ideal incompressible, that means inviscid, incompressible and irrotational flow. So let us recall few of the corollaries of the incompressibility and irrotationality in a flow field. Okay. Let us concentrate our analysis on a two-dimensional frame of reference. Let us take a two-dimensional x and y in a Cartesian coordinate system. We consider a two-dimensional flow in a Cartesian coordinate system described by x and y axis. Now in this case we know that an incompressible flow, for an incompressible flow, the equation of continuity, conservation of mass, for an incompressible flow is del u del x plus del v del y is 0, where u and v is the velocity in the x direction and y direction. That means velocity vector v has the component u and v in along x and y axis respectively. Now as a consequence of this continuity equation, we define a function, stream function. We have discussed in details about this earlier. Stream function psi, which is a function of space coordinates xy in such a way that the velocity components are defined like this. U is del psi del y and v is minus del psi del x. One is positive, another is negative. So that the psi function, that is the stream function, automatically satisfies the continuity. You see that if we substitute u and v from this definition, we get that this automatically becomes 0. That means stream function automatically satisfies the continuity. This we have already recognized earlier. Now you see that we know that for a streamline, the stream function psi remains constant along the line. Now if we recall the definition of a streamline definition, we know that the tangent to it at any point represents the velocity vector, and the equation of a streamline is that dy dx in a two-dimensional frame is equal to v by u, because the slope of this streamline gives the direction of the velocity vector. So for a two-dimensional case it is like this, which gives the u dy minus v dx is equal to 0. This is nothing but the equation of a streamline. Now let us see that if we expand psi in a differential form, we can write d psi being a function of both x and y, we can write del psi del x dx plus del psi del y dy. Now del psi del x by definition is v minus v, and del psi del y by definition is u dy. Since the equation of a streamline, that means along a streamline u dy minus v dx is 0, so d psi is 0. So along a streamline d psi is 0, that means psi is equal to constant. So therefore we know that the streamlines, for example, if these be the streamlines at any instant, in a steady state the streamlines remain same at all instant of time. So psi is equal to constant, that is psi 1, let this is psi 2, let this is psi 3. That means we can ascribe a single value of psi for each and every point along a streamline. So this we have discussed earlier. Now if the flow is irrotational, now in a two irrotational flow means we have discussed earlier, that is a flow where rotation is 0. So rotation has got three components along the three axis, coordinate axis. Now in a two-dimensional flow there is only one component of rotation, that is the rotation about the z axis. How do you define rotation? We defined it earlier that rotation is the arithmetic average of the angular velocity of two linear segments which were initially perpendicular to each other. That means if we take a point P and AP and BP are the two linear segments mutually perpendicular to each other, then because of the flow field, this tendency of rotation of these linear elements in the opposite direction, for example, if we take the arithmetic average of the angular velocities of these two linear elements, we get the rotational component, and we have already derived earlier this with respect to z axis, that means an axis perpendicular to the plane of this figure. That means at P the axis is perpendicular to the parallel to a z axis here, which can be represented like this. It will be half del v del x minus del u del y. Now we can recognize the other component of the rotation, that means x, that means in yz plane, rotation in yz plane. This is rotation in xy plane, that is rotation about z axis. Rotation in yz plane, that is about x axis. Rotation like this, it will be y and z, that means del w del y minus del v del z. Rotation in about x axis, that is omega x, del w del y minus del v del z. Similarly with respect to y, it will be del u del z minus del y, it is, that means del w del x, del u del z minus del w. So three rotational components, and for an irrotational flow all these three components become independently 0. For a two-dimensional case we don't come across this defined in an xy plane, so rotation is only this, so this becomes 0. So these three together is written in the form, if you recollect, is 0, where v bar is the velocity vector, which has got three distinct components u, v and w. Now for an irrotational flow, del v del x minus del u del y is 0, or we can tell that curl of velocity vector is 0. Now a consequence of this mathematical relationship is that this vector v can be expressed as a gradient of a scalar function phi. So this is a mathematical theorem that if curl of any vector is 0, that vector can be obtained or can be expressed as a gradient of a scalar function. So this scalar function phi is known as the potential function. If this vector is the velocity vector, in case of irrotational flow, curl of this velocity vector is 0, then velocity vector can be obtained as a gradient of the scalar function phi, which is known as velocity potential function. Velocity potential function, or simply velocity potential. Now, a negative sign is deliberately used to make the thing similar to all phenomenological equations where any flux is proportional to the negative gradient of the potential function. So therefore a negative sign is implied. So for that, if you just expand this, then we can write for three-dimensional cases with respect to a Cartesian coordinate system. Simply we can write u is equal to minus del phi del x, v is equal to minus del phi del y, and w is equal to minus del phi del z. So for a two-dimensional case, we can deal with this two, u is equal to minus del phi del x, v is equal to minus del phi del y. And the curve or the line along which phi remains constant is known as equipotential line, is known as equipotential line, equipotential line. Now let us find out the equation of equipotential line. The equation of equipotential line means phi is equal to constant. This is the equation. But we try to derive it in terms of u and v. What to do? You write it in a differential form, that d phi is 0. Now what is d phi? D phi is, because phi is a function of x and y. This is a scalar function, point coordinate x and y in case of two-dimensional system. In three-dimensional flow, it is a function of x, y and z. So it is del phi del x dx plus del phi del y dy, and that must be equal to 0 along a equipotential line. So del phi del x is minus u, del phi del y is minus v. So therefore we see u dx plus v dy is 0. So this is the equation of equipotential line. Equation of equipotential line. Equation of equipotential line. Similarly, equation of streamline is v dx minus u dy is 0. This is the equation of streamline. This is the equation of streamline. So immediate inspection of these two equations said that they are mutually orthogonal. They are perpendicular to each other. U dx plus v dy is 0, and it is v dx minus u dy is 0. The slope of this line at any point and slope of this line at any point are perpendicular to each other. So therefore, we can say that if these be the streamlines, these be the constant streamlines, psi 1, psi 2, psi 3, psi 4, then the orthogonal families of curves will be the constant phi lines. So they will be, these corners will be 90 degree. So they mutually form a orthogonal sets of trajectories. So this is constant psi line, these are the constant phi lines. Now we come to the concept of circulation. What is meant by circulation? What is meant by circulation? Let us consider in a flow field a closed loop and bounded by a closed contour. Now if we designate some small elemental length as ds, where the velocity vector is v bar, then the contour integral of this v dot, let us define a vector, normal unit vector along the tangent to this, that means along the tangent to the curve at this point, that means along the direction of this linear element ds, and unit vector n1 we define, then n1 ds, which means that the elemental ds is given a vector concept by multiplying it with a unit vector along the elemental length, that means along the tangent to that length. Then this quantity, if we make a contour integral over this closed contour, then we define this as the circulation, gamma, which is the symbol. So gamma is the circulation. Circulation. It simply means that the length, linear elemental length multiplied by the component of the velocity along that length. So velocity vector may have in any direction component of the velocity vector along that length, and if we sum up all such quantities, product of the velocity component along a linear, along a infinite small elemental length, and product of the length times the velocity component along that direction and sum it up over a closed contour, then this is known as circulation around that closed contour or closed circuit. This is known as circulation. Okay. Now we can show that the circulation for any closed contour can be found out by the circulation of small grids or small contours generated within that big contour, closed contour. That means, for example, if this closed contour is now divided into a number of small circuits, this big circuit is divided into a number of small circuits, and you see that if we have the velocity component like this, now what happens? Before that, I must say that when we make this integral, we take certain direction for this integral along the closed contour. If we make in this direction, usually taken as positive conventionally, so this is given a direction like that, a contour integral or a closed contour integral along a closed contour is given with a sign, so this is positive along this sign. That means conventionally taken the anti-clockwise direction, or rather this way you take an anti-clockwise direction. This is not anti-clockwise, so this is an anti-clockwise direction. Let us consider the anti-clockwise direction. That means this direction, anti-clockwise direction, as a positive. Now you see, therefore, for a small circuit, therefore the circulation will be defined the velocity vector multiplied by this length, velocity vector multiplied by this length, this velocity vector multiplied by this length, this velocity vector multiplied by this length. Now you consider the common edges. That means this edge, the contribution of the velocity at this edge in the circulation for this grid is in one direction, and for this grid is in other direction. So for all these common surface, it is like that. It contributes in the calculation of circulation for one grid, one closed circuit in one direction and another adjacent closed circuit in another direction, so that they ultimately nullify each other or cancel each other, and we are left only with these contributions along the outermost boundary. So that ultimately if we sum up the circulations of these infinite small circuits, we get the circulation around the closed circuit. Now let us find out the circulation in case of a xy coordinate. Let us see a simple case. Consider a circuit. We can choose a circuit, a rectangular circuit like this, of length dx and length dy. What will be the circulation? Let us consider at this plane the velocity is u, and at this plane the velocity will be changed for a distance dy will be u plus del u del y dy. Similarly, let us consider the velocity at this plane will be v, positive direction. So velocity at this plane will be changed for a distance dx as v plus del v del x dx. Now let us find out the circulation with the anti-clockwise direction as the positive direction. Now what is this? This will be u for this length, this elemental length, u into dx, and this has got an anti-clockwise rotation about any point within the circuit. This is the way the direction for the rotation has to be taken care of. Similarly, for this element, it is the velocity along this element is v plus del v del x dx. U doesn't have any component for this which is perpendicular to this linear element. So therefore, it is the velocity component along the linear element times dy. This gives also in the same directional notation. So plus v plus del v del x dx times dy. Then for this, it is an opposite direction, but the magnitude is this velocity component times the length dx. That means minus u plus del u del y dy. This is the velocity component times dx. Minus this one in the same direction, that means minus v times this length dy. So if you make it simple, so it will become ultimately del v del x minus del u del y into dx dy. This is because you see v dy cancels, u dx minus u dx cancels. But this is our twice the rotation, and this is, you know, is the vorticity about the z axis. We earlier defined vorticity is the 2 times the rotation vector. If you represent vorticity as a vector, then it is 2 times the rotation vector. So this is the vorticity, so vorticity times dx dy. What is dx dy? Dx dy is the area of this contour. So we can tell that circulation divided by this area is the vorticity. All right, this is vorticity. So this is a very important theorem from which we can write that vorticity